I'm talking to Professor Mark Hindmarsh, Professor of Theoretical Physics at the University of Sussex. Thanks for coming in, Mark.
It's a pleasure.
I often ask the people I interview what type of scientists they are. Now, I've already introduced you as a theoretical physicist. I hope this is not a difficult question, but what does a theoretical physicist do?
Well, the theoretical part means that I use the tools of mathematics to discover things about physics. And so whereas an experimental physicist might use a laser in a lab, it's mathematical ideas that theoretical physicists use to explore the universe.
So an experimentalist might be working on the frontiers of what's available now, but you're sort of using those tools for future ideas, really.
Well, that's part of the game of the theoretical physicist, and some of the things that I'm interested in might not be experimentally accessible for 40 years, or even might not exist at all, but that's the risk you take as a theorist.
So what is the draw then? Is it the solving puzzles? Or
solving puzzles and just the beauty of ideas, the way that nature is so unreasonably mathematical in the phrase.
And is this something you've been interested in from a child? I mean, you got into science when you were very young?
Yes, I think it was astronomy that was my gateway drug into physics, and particularly in the 1970s in Britain, there were a lot of dark periods. There were some industrial unrest between management and workers in the power industry, and so that meant beautiful dark nights where I could go out into the garden with my telescope and look to see what there was to see.
It is a shame actually about light pollution a bit, especially down in the south of England, isn't it?
It is, yes. It's
especially for astronomy. Now, I have to sort of start with an apology because I know I'm going to use the word gravity waves instead of gravitational waves. And I know your research is based on this, or part of it. Gravity waves are easy. You go down to the beach and the waves on the sea are gravity waves. But what are gravitational waves?
So gravitational waves are waves in the structure of space itself. So if a gravitational wave went through between us, of a very large and unrealistic amplitude, but the distance between us would change. We'd get closer, we'd get further. And that's actually the structure of space itself that's changing as a gravitational wave goes through.
Space-time, presumably.
Space and time, because as we know, they're linked.
And how do you make gravity waves?
Well, you need to get an enormous amount of mass and accelerate it very quickly.
Right.
So normal terrestrial processes don't really generate gravitational waves at any detectable level. But out there in the universe, there are very dense, very fast-moving objects. So the closest ones are probably binary neutron stars, or perhaps even binary black holes, somewhere in the neighborhood of the of our galaxy.
So if you have something like, you see these pictures of Jupiter, which looks like a perfect sphere turning. Something like that wouldn't produce gravity waves.
So a perfect sphere does not produce gravitational waves. You have to have some kind of asymmetry. So it's perhaps thought that a mountain on a neutron star could radiate at some level. But as I was saying, the most detectable source for the near future is probably a binary neutron star.
So two stars are quite, normal two stars are quite massive and far apart. With the neutron stars, because they're very small and dense, they can get close together, so they can spin faster.
And so their orbit might be, their orbital period might be just 1,000th of a second or something.
Very, very massive. Fast-moving objects. Because I think you told me that the energy density goes up as the speed to the power 6 or something.
The power in the gravitational waves goes as something like the frequency to the power 6, yes.
So the faster rotating objects are producing more power, so they're easier to detect, presumably.
Exactly, yes.
Okay, so how would you detect them?
So you have to measure the distance between two objects, like you and me, very accurately. So you and me, we're not particularly well-defined and easy to do experiments with, and we might get a bit bored, but what you need is some kind of large mass and measure the distance between that, and the way it's done is with a laser beam, a laser interferometer in fact.
Right, okay. So you have two large masses with a laser with some kind of interference. As they move, you see the changes in the interference pattern.
Exactly. The way to set up the interference is to have two arms at right angles, something like this. You have masses at each end and masses at the center, and you can interfere the laser beams that are set up between them, and it's rather like the Michelson-Morley
Yeah,
experiment.
yeah.
You can tell the difference by the small changes in intensity of the laser beam where they cross.
Yeah, and these exist, these experiments, don't
These
they?
experiments exist and are going on right now.
Yep.
The biggest of them is in the United States. It's called LIGO, stands for Laser Interferometer Gravitational Wave Observatory.
Yep.
And it's right now it's going having an upgrade and coming back in 2016,
Right.
where people are hoping, with their fingers crossed, that we'll see some of these binary neutron stars.
And these can detect tiny movements, can't they?
It's
Absolutely.
extraordinary. It's quite extraordinary, the accuracy that these instruments have. So if you talk about in terms of strain, that's the fractional change in length that they can detect. It's 1 part in 10 to the 22, which translated into a physical unit is about 1,000th the diameter of a proton.
So the atoms and molecules being hot, of jittering around, you have to cool these things, presumably, do you? Or
That's part of the upgrade that's going on. They're installing cooling, so you have to worry about the thermal jittering of your instrument. You have to worry about the earthquakes, so just seismic noise.
it'd be a brilliant seismograph.
And you also run up against the sort of the quantum nature of light itself. I mean, there's a kind of the laser beams are made up of photons, and they're hitting the mirrors at either end of your interferometer like a sort of pattering of hail or something.
And very briefly, there is a project to go out into space with an experiment, isn't there?
There is. That would be the next stage. It's be sometime coming in 2034, but
Right.
the plan is to fly laser interferometers on satellites with an arm length of not 4 kilometers, but approximately 1 million kilometers.
Wow, and that much more sensitive as a result.
So it'd be, the sensitivity will be similar, but it'd be accessing a different frequency range,
Okay.
which would be interesting for example, binary white dwarfs, about which we know much more than binary neutron stars.
Oh, I see. So we have gravitational waves,
Thank you.
sorry. And your research, part of your research, tell me about that.
So I'm interested in the gravitational waves that come from the very early universe. That's my research interest. I try to understand the first few fractions of a second of the Big Bang, where energy densities were huge, and we have access to physics far beyond the energies of any conceivable particle physics experiment on the Earth. So one of the interests is looking for violent processes that are happening very early on in the history of the universe.
How early on are we talking about?
So one of the, I think what we're going to look at later is something that might have happened at about 10 picoseconds after the big,
There's a
very
millionth of a
instant.
millionth of a second after the Big Bang.
It's quite a short time by terrestrial standards, but quite a long time after the Big Bang by particle physics, cosmological standards.
Yeah.
And the particular interest of this epoch in the history of the universe is that it's the time at which the Higgs field would have turned on.
Okay.
So the Higgs field is the field that permeates everything. It gives particles mass. It tells particles what mass they should have. And we've heard in the last couple of years a lot about the discovery of the Higgs particle. The Higgs particle is like a ripple in the Higgs field. And through the magic of quantum theory, we understand that ripples in fields we can actually think about them as particles as well.
Okay. So we've got an image, I think, coming up from your work. Can you give us an outline of what it is you calculated then in this work?
So we did the first large-scale numerical simulation of the Higgs field turning on in the early universe, which includes all of the relevant physics that we understand now on the basis of particle physics. So this process of turning on would have been rather like, it is a phase transition.
Right.
And we can draw very strong analogies between the phase transition, say, between liquid water and steam, and the phase transition of in the Higgs field.
So effectively, after the Big Bang, very soon after the Big Bang, was the temperatures if you can talk about temperatures, was too great for the Higgs to form, or it wasn't stable. And then suddenly, as the universe expanded and things cooled, new physics was allowed to appear. Is that right?
Yes, I mean, we can think about the phase, the hot phase with the Higgs field turned off as being like the vapor phase in water,
right,
and the cold phase with the Higgs field turned on,
right,
as being like the water phase. And so as we cool a water vapor, we see droplets of water condensing and growing, and eventually our system turns entirely into liquid water.
And there's a change in energy because of that, isn't there?
There's a change in energy. There's a latent heat that's released as this goes on.
So looking at the image here, so we're looking at the whole universe here now.
We're looking at a small portion of the universe,
Oh, okay.
and we're looking at the energy, the kinetic energy, the motion of the surrounding fluid that the Higgs field would have set up as it condensed.
You mentioned this when we were talking earlier about this idea of a room full of gas and someone flicking a switch.
Yes, that's another kind of phase transition that actually it gives some of the idea of the possible violence of the transition. So if you're in a room, if you've left your gas on, you come back and are foolish enough to try and investigate what's going on by lighting a match, you'll set off an explosion. And in very slow motion, what happens is that a flame front propagates out at very high velocity from the initial spark and turns the gas-air mixture into burnt gas behind the flame front. So what we're going to see is sort of the analogy of a flame front.
So we've got a video here we're going to play, and you can talk me through this.
So there's the spark which sets off the Higgs field condensing, and then it's joined by many others, and you can see that the expanding bubbles of Higgs field grow and merge, and what we see represented in the colours here is the kinetic energy of the fluid. So it tells you how much the fluid is around is moving around.
So this
moving in the early universe.
This energy that's released, or this change in energy, because of this phase change, how much of that is? What percentage of the energy in the universe does this represent?
Well, so that's unknown at the moment.
Right.
So we're just kind of on the threshold, thanks to LHC, of understanding exactly how much energy is available at this epoch of the universe. Now, I should caution you that because we don't know the exact nature of the way that the Higgs field turned on, this energy might be very, very small, and we might not actually be able to see anything. This is one of the risks of being a theorist,
yes,
working right at the frontier.
So the relation to gravitational waves is that this explosion, effectively, what it looks like an explosion, is going to produce gravitational
exactly.
waves.
The motion of the fluid, they're actually sound waves, really, that are being generated by these explosions. Yes. These sound waves collide and generate gravitational waves, but it's could be a huge, relatively speaking, huge 1% fraction of the total energy density of the universe involved in these sound waves, in these bangs.
Yeah. So this is obviously interesting from its own point of view, but there was a result in March 2014, wasn't there, just recently, which is related to this, isn't it?
There is. It's very. We're talking at a very exciting time in early universe cosmology, because the first evidence for gravitational waves out there in the universe was published, right, in quite a different experimental area. It was looking at the cosmic microwave background. Yes. It's an experiment called BICEP, or in its second incarnation, BICEP-2. And by looking at the patterns of the polarization of the cosmic microwaves, which were left behind by the Big Bang, they deduced that out there in the universe there were some very long wavelength gravitational waves.
Right. So this is the first evidence, really, of gravitational waves. And then how does that relate to your calculation?
So well, first of all, what it means is that there are gravitational waves out there in the universe from the early universe to discover, and it makes a concrete prediction for something to go and look for at higher frequencies.
Right.
because the process which generated these gravitational waves is called inflation, which happened very, very much earlier on than the time we've just been talking. That's a billionth of a second, 10 to the minus 36 seconds, right at the beginning of the Big Bang.
Yep.
And this would have made gravitational waves on all frequencies.
Yes.
So that there's something for a space-based detector to go and look at.
Right. And that will affect your predictions.
So in some sense, this gravitational wave background is different, and is sort of a noise which might obscure what we're looking for. Of course, our gravitational wave spectrum that we were just discussing from the bangs have a very pretty definite frequency, and so hopefully they would poke up above the background noise that was set up by inflation.
Yeah, absolutely fascinating. Thank you very, very much for talking to me about gravitational waves. Is there any particular principle or idea you found in your career that you found very helpful, sort of scientific idea or result or something like that, that you think really has inspired you in your work, for example?
I think the inspiration probably came from my supervisor, my PhD supervisor, a guy called Tom Kibble, whose ideas were very much actually instrumental behind the what's now called the Higgs boson, and he was unfortunately, because of the law of threes, not recognized by the Nobel Academy last year, but his approach to physics of caution, modesty, but very insightful physics was quite an inspiration to me as a PhD student.
Thank you very much for talking to me.
Thank you.